In this video, we present our work towards understanding time-varying spatial 3D data analysis with animation and small multiples in virtual reality and desktop. What's spatial 3D data? It's information captured across width, height, and depth, with spatial relationships playing a crucial role. Time-varying spatial 3D data, which we refer as 4D data, extends this concept by incorporating temporal dynamics, representing a sequence of spatial 3D data over time. S4D data is common in many domains involving real-world phenomena, such as ocean science and atmospheric science. However, analyzing S4D data is difficult. Specifically, checking the evolution of complex 3D spatial patterns over time requires users to process and synthesize large amounts of information, which can exceed human cognitive, perceptual, and comprehensive ability. Visualization has been proven to be an effective approach in supporting spatial temporal analysis since it can transfer abstract data into perceivable and interactive visual representations. Existing research has proposed different S4D visualizations, which can be classified into animation and small multiples. These visualizations have been tested in desktop and VR environments. Despite these initial attempts, a recent survey highlights that current visualizations are insufficient and calls for more effective visualizations. However, to fulfill this call, we currently lack explicit studies on the strengths and weaknesses of existing visualizations. As shown in this table, there are no studies to evaluate the two types of visualizations and the two environments at the same time. Moreover, from users' perspectives, we also lack a deep understanding of their real-world needs that future visualizations should support. Therefore, this research aims to answer three questions. First, what are the strengths and weaknesses of the four existing visualization techniques? Second, what are the analytical tasks, current practices, and challenges? Third, what are the research opportunities for designing future S4D data visualizations? Now let's introduce our study design. We first visualize spatial 3D data at one timestamp as a cube with standard direct volume rendering and isosurface rendering to provide both global and local context. Building upon the S3D cubes, we design four S4D visualization techniques across two visualization types and two displaying environments. For VR animation, all S3D cubes are placed in the center of the field of view. Each cube appears for 1 second before disappearing. For VR small multiples, multiple S3D cubes are arranged in a horizontal half circle wrapping around the user. The desktop animation is similar to VR animation, with all cubes placed in the center of the desktop screen. For desktop small multiples, we follow the common practices for creating small multiple for 2D by arranging the cubes on a flat grid on the screen. For all four techniques, we provide a set of interactions, such as spatial slicing, temporal filtering, and 3D manipulation. We utilize a real-world dataset that spans 30 days and includes daily records of dissolved oxygen level in the seawater in the Pearl River estuary and adjacent shelf in China. This dataset captures the pre-typhoon, during typhoon, and post-typhoon periods, offering insights into how typhoons impact oxygen levels across various ocean locations over time. With the datasets visualized by the four techniques, we invited 12 researchers with experience in spatial temporal data analysis from diverse fields to attend our study. Our study had 3 stages: introduction, open-ended exploratory study, and semi-structured interview. We used the 4 techniques to elicit user feedback on their pros and cons. Therefore, the task is not a race for completion time and accuracy, but an open-ended exploration to extract insights. We analyze the qualitative feedback to answer the 3 questions. We will highlight some of the findings. First, The four techniques have some shared strengths and weaknesses. Participants emphasize that 3D visualizations are essential to deal with S4D data, especially when they wanted to observe volumetric distributions or irregular spatial shapes. As to the shared weaknesses, participants reported moderate to high levels of mental demand and effort across all four conditions, which means none of the four visualizations fully alleviate the mental demand of interpreting complex X4D data. Besides, we also observe large interquartile ranges and wide variances across the questions that assess user experience. The results indicate that the four visualizations fail to deliver a consistent user experience, and their success may depend on individual user capabilities, such as the spatial ability or VR familiarity. Regarding the visualization types, animation and small multiples have complementary strengths and weaknesses. For example, animation is good at observing continuous changes, but struggle with direct comparison. On the contrary, small multiples enable direct comparisons across discrete time points. As for the displaying environments, users suggested that VR has the potential to support internal spatial exploration, but the current techniques fall short in realizing this potential. Now let's take a look at analyst needs. Based on participants' responses, we categorize the tasks along two key dimensions, spatial focus and temporal scope. The spatial focus can be single subspace or multiple subspaces, and temporal scope can be fixed time and dynamic time. Based on the two dimensions, we categorize tasks into four main categories, as shown in the table. To perform these tasks, we find that our participants typically adopted a two-step process: dimensionality reduction to 2D spaces, followed by detailed and overview analysis based on the selected subspaces. They reported that their selection mainly relied on existing understanding of the data and the research context. Such an approach analyzing complex 3D phenomena with 2D reduction introduces two challenges. First, it is difficult to efficiently select subspaces for investigation. Our participants often struggled to determine where to focus, relying heavily on trial and error manual methods. Second, the 2D representations cannot fully capture inherently 3D features, such as volumetric distributions or irregular shapes. For example, in ocean science, researchers are interested in phenomena like water masses, defined band density, salinity, and temperature. The changes between water masses are abstract in 2D, but in 3D, their spatial volume and interactions become clear. Based on the understanding of existing techniques and analyst needs, we propose several research directions. Enhancing VR usage in S4D visualizations, supporting analytical tasks by addressing unique data characteristics, embedding intelligent support to find subspaces deserving investigation, and reducing the overwhelms while maintaining 3D structures. In conclusion, our contributions are threefold. First, we conducted an exploratory study involving four S4D visualization techniques, providing insights into their strengths and weaknesses. Second, we summarized the analytical tasks, current practices, and challenges for S4D data visualizations. Third, we identified multiple future research directions. For more information, please refer to our paper. Thank you for watching.